The rest of this chapter deals with systems of equations. A system of equations is any group of equations in the same variables. So it can be 2 equations, which is most common, or 3 or 4, but we've got the same variables regardless. The solution, therefore, to a system of equations is any ordered pair that will make all of the equations in the system true. For the most part, as I said, we will be dealing with systems of 2 equations. So if you look at this first example, here are the 2 lines. They intersect at a single point. This is the most common type of system of equations, and we just have to be able to identify that point. If you look at the next one, if you notice, the slopes on both of these equations are the same. Here it's easy to see as -1/2. On the other, remember that the slope is -a over b. And so in this case, that slope is -1 over 2. Equal slopes produce parallel lines, so there are no solutions to this equation. And then the last system of equations is coinciding lines. What that means is that one line lies directly on top of the other. If you take a look at these 2 equations, I can take the first equation, I can multiply every term in this by -2, and if I do that, I'll get 6x minus 10y equals 12. So I have the exact same lines. Coinciding lines have infinitely many solutions. Any system or any systems of equations that have the same solution are equivalent systems. So regardless what the coordinate is on the solution, if their solutions are the same, then the systems are equivalent to each other. The next thing talks about transformations. Transformations are when you multiply, add, do various things to the equation. So just like we saw on the last slide, if you multiply any equation by some value, that equation is the same. If you substitute for one variable something that's equivalent, it's the same. So if I say that y is equal to 6x, I can plug in 6x in any place that I see y in the other equation. And then I can also replace any equation by the sum of that equation and another. So if you add 2 equations together, you can replace that in the system as well. These things start to show up as we begin to solve systems of equations. So to get started, we're just going to identify solution to a system. Is the point 5,2 a solution to this system? This is a very, very simple problem. You won't even see this on a test. You plug 5 in for x, 2 in for y, and you see if they work. So this would be 2 times 5 plus 3 times 2 equals 16. And you plug in 3 times 5 minus 7 times 2 equals -1. This becomes 10 plus 6, and 16 is equal to itself. So it's definitely a solution to the first equation. This is 15 minus 14. Is 1 equal to -1? It is not. So this is not a solution to the system. The next asks, are the following systems equivalent to each other? That means, do they have the same solution? For the first system of equations, x equals 5 and y equals 3x, I can substitute. So the solution to this system is 515. On the second system, I'll have to do a little bit more. I think for this one what I'll do is I will add x to both sides of the first equation, and I'll get y is equal to 10 plus x. Then I'll substitute this information in for y here. So that's 10 plus x plus x equals 20. So that's 10 plus 2x So the x value on this solution, on this system, is 5. I then have to plug 5 in to either one of those equations. It doesn't matter. And for x, so y plus 5 equals 20. So the solution on this system is 5, 15. So these systems are equivalent. For the next problem, we're going to solve using a method called substitution. You actually saw me do that on the last problem. We want to solve one of these equations for either x or y. It doesn't matter. When you're making this decision, solve the equation that's simpler. I'm going to solve this equation for x because if I solve it for y, it's going to take more steps because I would have to deal with this negative. But if I solve for x, all I have to do is add y to both sides. So this equation becomes x is equal to 9 plus y. I will then substitute 9 plus y in place of x. So I get 2 times 9 plus y plus 3y is equal to 13. I'm not finished. All I have right now is a y coordinate. I then plug this y coordinate into either one of these equations and solve for x. In this case, I'm going to choose this equation, again, because it's a simpler equation. So I'm going to take that negative 1, I'm going to put it in place of y. X minus negative 1 equals 9. That becomes x plus 1. And that means that x is then equal to 8. The solution to this system is 8, negative 1. The next method we'll look at is called linear combinations or elimination. This is the idea that I can add these equations together for the purpose of eliminating one of the variables. That's one of those transformations that we talked about that will produce an equivalent system. If I add these two equations together just as they are, I get 5x minus 3y is equal to negative 25, and that does absolutely nothing. So what needs to happen is I need to multiply either one or both of these equations by any constant I want, so that either my x's will eliminate or my y's will eliminate. There are many ways to solve this. I am going to choose to eliminate my y's, and the reason is because one of them's positive, one of them's negative. You could very easily eliminate the x's as well. It's really a personal preference. What I will do is I will multiply the first equation by 5, and I will multiply the second equation by 2. When I do that, I get 15x plus 10y is equal to 20. 4x minus 10y is equal to negative 58. Now when I add these equations, 15x and 4x become 19x. 10y and negative 10y eliminate. And then 20 and negative 58 become negative 38. When I divide by 19, I can figure out that x is equal to negative 2. Again, I'm not finished. I still need to solve for y. It doesn't matter which equation you use. Pick the one you like best, plug negative 2 in place of x, and solve for y. For this equation, or for this system, I'll use the top equation. So I'll say 3 times the negative 2 that I've calculated plus 2y is equal to 4. So the solution is -2, 5. We will look at solving by graphing on your graphing calculator in class. This next section uses systems of equations with word problems, and the hardest part about this is getting the equations written correctly. One thing that I strongly suggest is identifying your variables at the very beginning. And the way that you'll identify them is by looking at the question. How much does each pen and each pencil cost? So what I'm looking for is the cost of a pen and the cost of a pencil. So I might say I'm going to let X equal the cost of a pen, and I'm going to let Y equal the cost of a pencil. Now, I have 8 pens. That's 8X. I have 7 pencils, so that's 7Y. And I'm told that it's $3.37. Then I've got 5 pens, and I've got 11 pencils, and that costs $3.10. Now I can solve this, and you can use any method you'd like based on the setup of this equation. I think that solving by elimination is probably the best option. I notice that if I just add these together, nothing eliminates. So I will multiply this first equation by 5. I will multiply the second equation by -8 because I want to eliminate the x's. And I need one of them to be positive and one of them to be negative. So my top equation becomes and then the second equation when I add them together, 40x and -40x eliminate. 35 minus 88 gives me -53y. And then 16.85 minus 24.8 give me -7.95. When I divide, I find that y is equal to 0.15. Of course, I'm not done. I need to find the value of x. So now I have to relate this back to the problem. X is the cost of a pen. Y is the cost of a pencil. So a pen costs 29 cents and a pencil costs 15 cents. For the next problem, when I start to identify my variables, I'm going to first look at my question. How many colored marbles does Lauren have? So I'm looking for the amount of marbles. So I will let x equal the number of plain, and I will let y equal the number of colored. She says, or we know, there are 32 more plain than colored. So if I have to think about this, if I have 5 colored marbles, how many plain marbles would I have? Well, 5 plus 32. So I can say that x is equal to y plus 32. Okay, the number of plain marbles is equal to the number of colored and 32 more. The next part says that there are 180 total. Well, so if I take the number of plain plus the number of colored, I will have 180. This problem lends itself very nicely to substitution. I can plug in all of this in place of x. So according to this problem, y, the number of colored marbles, is 74. That is exactly the question I was asked. I do not have to go any farther. This last problem is one that's very challenging, so I'm again going to direct you, once you have read the question, or once you've read the whole problem, go to the question. How many of each size gift basket should you make? This tells us that my variables need to be the number of small gift baskets and the number of large gift baskets. Now that I have this, my two equations are going to represent what I have information on. I have 58 pounds of chocolate total and 36 jars of nuts total. That means that my first equation is going to be the amount of chocolate used per basket to use up all my chocolate. Well, it says here that the small basket uses 3 pounds of chocolate, so that's 3x. The large basket uses 4 pounds of chocolate, so that's 4y. And altogether, I have 58 pounds of chocolate. Now I will write an equation to represent the jars of nuts that we have. The small basket uses one jar. The large basket uses 3 jars. And altogether, I have 36 jars. Now that I've got this information, I can solve the equation, or solve the system. I see here I've got two equations in standard form. For this, I will again use elimination. I will multiply this bottom equation by -3, because then I can eliminate the x's. My new system becomes 3x, 4y equals 58, -3x minus 9y is -108. When I combine these, my x's cancel. So now I see that I need 10 large gift baskets, and that I can plug this in to find out the number of small gift baskets. So they should make 6 small baskets and 10 large.